out of that, you get the acid dissociation constant. And for this species, it's 10 to the minus 35. So roughly this equilibrium, if you want to just globalize it, is terrible. Okay? It's totally on the left. Okay? So amines are incredibly lousy acids, okay? Because the corresponding amide anions are very strong bases. And we know that. That's why we use diisopropylamide as a strong sterically hindered base. Okay? And the pKa, therefore, is 35. Okay? Now, this contrasts with alcohols, where this is an oxygen, much more electronegative. The pKa is 15. All right, so here's the preparation of aldehyde. It's pretty straightforward. You take this guy and pull off this proton. It's not easy to pull off this proton. You need a stronger base than the corresponding conjugate base of this, which is aldehyde. And what is stronger than aldehyde? We only know one base that does that, butylithium. Okay? Because that, when it gets protonated, makes butane. And that's an even lousier acid than the corresponding amine. Okay? So butylithium, the reason that it's butyl, I mentioned this before, is because it's easily made, and so it's just because it's commercially available and cheap. People use butylithium. You could have used any other alkyl lithium, but that happens to be the cheapest because it's the most mass produced. And out comes butane, and that makes aldehyde. That's how you get aldehyde. And specifically for aldehyde, the pKa is even a little worse. It's 36, not 35. Okay, you can call it 35. Corresponding to this, one can make other amide anions. In particular, we've used solamide sometimes in the past as an amide anion source. And that one is not made, although one could make it from butylithium. It's not made from butylithium. It's cheaper to make it from sodium metal and ammonia. And interestingly, in this reaction, it's a reduction of ammonia, and you get hydrogen gas coming out. You need a catalytic amount of iron-free chloride, and iron salt that act as an electron shuttle because it's an electron transfer reaction. Obviously, sodium gives up an electron, becomes sodium plus. In this case, solamide. This may look exotic, but it's not at all. It's exactly the same reaction as sodium with water. This is sodium with water we've done in high school, maybe. Some of you, many of you, and perhaps in Chem 1. Okay. At physics, because it's quite violent, sometimes it catches fire because the hydrogen evolved. It gets so hot that the hydrogen evolved in air catches fire. And so that makes sodium hydroxide and hydrogen. This makes sodomide and hydrogen. So that's another way, another base that occasionally we have used. But really your default base is aldehyde. You can't go wrong with that because it's sterically hindered. So you have no complications with other things, particularly nucleophilic substitution reactions. Okay, so what about the basicity of the amines? We know amines are basic. So how do we assess that? Well, there are two ways of doing this. One is to actually set up a basicity constant where you react the amine with water to make hydroxide. But this has been dropped by organic chemists because they prefer to put everything on the pKa scale. So you can compare all of the acids, even if they're lousy acids, on one scale. And so instead, what they look at is the reaction of ammonium with water that gives the free amine and H3O+. In other words, they look at in order to get at the basicity of the amine, they look at the acidity of the conjugate acid. And the weaker the conjugate acid, obviously the higher its pKa, and therefore the stronger the corresponding base. So when we do the same exercise for this equilibrium and get the acid dissociation constant out of this, it's 10 to the minus 10, meaning, or the pKa is 10, meaning that ammonium is not a great acid, but it functions as a mild acid. Okay? But it's not a great acid because the corresponding conjugate base is a pretty good base. Okay? And so compare this to alcohols. It's more acidic than an alcohol by 5 units. So it's definitely from that perspective, it's a reasonable acid. But it doesn't come close to acetic acid, which would be 5, pKa of 5. Okay? So pKa 10, you should add that to your list of pKas that we have roughly used in order to order in your mind the relative acidities of things. We had carboxylic acids 5, now we have ammonium 10, and we had alcohols and water 15, and we had aldehydes and ketones 20, and we had esters 25, and we had amides 30. That's a nice increments of 5 scale, which hopefully is something that you keep in mind. So one can look at the details of this, and you discover something interesting that we haven't really considered much before. And it comes out the following. If you look at the pKa of ammonium, exactly, to several significant figures, it's about 10, as you would expect, 9.2. When you put a methyl group on there, the expectation is that the pKa should go up, because methyl is an inductive pusher. And we've used that at the beginning of the semester in electrophilic aromatic substitution. Methyl activates the benzene ring, and on top of it, it's an orthopower director, because it's a pusher. Okay? So pushing into this charge means that it makes the charge happier. And that means that the acidity should get worse, meaning that the pKa should go up. Okay? Does it? Yeah, it does, as you would have expected. Okay, everything's fine and dandy. Now let's put a second methyl on there. Okay? The effect should reproduce itself. Roughly, we should get, what is this, 1.5 pK units, so it should be 12.1. But it isn't. It still goes up, so that's good, but it's really a minuscule amount that it goes up. So clearly there's some other trend going on that counteracts the stabilizing force of the inductive effect. And you can go all the way to trimethylamine, ammonium, and you see now the pKa actually drops, okay, even though you've added a third electron-donating group. And the reason for that is that introducing alkyl groups, particularly hydrophobic alkyl groups, around a charge, disrupts the solvation shell around the charge. Okay? These salts, all salts, can only be brought into solution, well, all compounds for that matter, because of solvation. The solid molecules have to be able to surround the individual molecules, in this case ions, and therefore make up for losing the crystal packing forces that are part of the crystalline material. So when you take sodium chloride and you dump it into some drink, like a margarita, it will dissolve. And the dissolution is because water is an excellent solvator by hydrogen bonds to the sodium plus and the chloride anion. And the same thing for salts, ammonium salts. Okay? So if you start, compared to ammonium itself, start sticking in relatively bulky groups, anything other than proton is bulky, right? Then you're disrupting that solvent shell. And therefore, these guys become less happy because they're less stabilized by solvation. Yeah?
Is this kind of a similar trend to like oxygen, like oxides, tertiary oxide? Does that do the same thing?
Correct, yeah. This is why, very good, because you've already seen this once before when we talked about the acidity of alcohols. Remember, I would say 15, but 15 is actually for the unhindered alcohols. Tertiary butanol is 18 because the tertiary butoxide ion, because of the tertiary butyl group, has worse solvation stabilization. Okay? So the anion is worse off. It's unhappy relative to methoxide. And that's why when you start putting substituents on the oxygen, you start seeing a slight increase. So completely analogous effect. Yeah. And so that actually drives home the case that the fact that oxygen and nitrogen, alcohols and amines, a lot of it is the same, but numerically, quantitatively, things are a little different. If you compare ammonium, by the way, with oxonium, which is the protonated alcohol, because oxygen, of course, is much more electronegative than nitrogen, it really loathes having a positive charge on it. And so the pKa of that is like consulfuric acid or HCl, -3, much worse than a pKa of 10. Okay? Again, actually, when you go in all these comparisons from nitrogen to oxygen, the jump is roughly 15 pK units. We saw that when we compared carboxylic acids with carboxamides also. All right, so we can play the same games that we played with alcohols and more recently with carboxylic acids. We can titrate the pKa values by sticking electron withdrawing or pushing substituents in the vicinity of the charge. So I'm giving you a couple of examples to give you a feeling for this. For example, if you put 3 hydroxy groups around the nitrogen, they pull, they're electronegative, and they drop. The pKa drops. In other words, the ammonium becomes more acidic because pulling electron density away from a positively charged species makes that positively charged more unhappy. And so the pKa, it becomes more acidic. It tries to get rid of that proton and therefore that charge more actively. You may ask, this is a weird beast. Why didn't he pick species where the hydroxy is right next to the nitrogen 3 times? Okay? This is a bizarre hydroxyethyl derivative. And the answer is, you know the answer, although it's probably difficult to see. But if you imagine a hydroxy group being here, just one of them, you recognize it's a carbon with an amine substituent and a hydroxy substituent. That's nothing else but a hemiaminal. And hemiaminals are not stable. They lose water and make the, they lose ammonia and make the carbonyl. Or they can lose water and make the imine, depending on which way you go in the equilibrium. Okay? So they don't exist. But this one is stable. So another way to do this is to put a substituent on that has more S character in the bond to the nitrogen. And so we're comparing cyclohexane ammonium with benzene ammonium. Here we have sp3, that's normal, around 10. We replace this with sp2 hybridization, boom, you go down 5 pK units. Why? Because this has more S character. More S character means the orbital poles is located closer to the nucleus, or the electron cloud around that atom is pushed closer to the nucleus, meaning sp2 relative to sp3 is electron withdrawing. And so that shows up in a lower pKa. You can do this for amide. The amide is an interesting case. If you look at an amide, there's the lone pair on the nitrogen. So if you just look at this as an amine and ask the question, what's the pKa of that? You would have to be able to protonate at that position. But you can't, because it protonates on oxygen. And in part, this is, of course, because of protonating on oxygen, you get a resonance stabilized cation. But the corollary of this, or the complementary explanation, is that in the starting material, the starting amide before protonation, that lone pair is no longer really available because it's donated into the carbonyl. So you have a lot of dipolar resonance character, with this being a CN double bond. As we shall see later on in the last chapter, peptide, the peptide bond, because of this, actually is hindered to rotation. And in the NMR, you see cis and trans isomers because the rotation around this alleged single bond, which is not really a single bond, it's more like a 1.6 double bond or something like that, is hindered. It's slow on the NMR timescale. So here, of course, not unexpectedly, the pKa of that is 0.63, so this is a very strong acid. In other words, it's very difficult to protonate relative to a normal amine to protonate an amide. Okay? That lone pair just isn't there. Then, rather than having an sp2 hybridized substituent, we can rehybridize at nitrogen itself. Okay? And that's an imines. So imines, the nitrogen is sp2 itself is sp2 hybridized. And so the question is, how easy is it to protonate imines? And you find that the pKa of imines is about 1,000 times more acidic, or more than that, a few thousand times more acidic than a normal ammonium, because this is sp2 hybridized. So this is a pKa of 7 to 9, a few units lower. And much more pronounced when this is sp hybridized. This is our nitrile compound when it's protonated, a reaction that we did last Thursday when we did the mechanism of hydrolysis of nitriles to carboxylic acids. Remember, the first step was protonation on that nitrogen. That's actually a lousy step. If you wanted to do this such that you actually put the protonated nitrile into a bottle as a salt, you would have to use an extremely strong acid, magic acid as they're called, the special acids that pull this off. Of course, we don't care about this when we do the hydrolysis, because all we are setting up is the equilibrium. As long as you can protonate in an equilibrium concentration, you're okay. But if you measure, I'm not sure this has actually ever been accurately measured, but the estimation is less than -5, which means this is about potential, like concentrated sulfuric acid or fuming sulfuric acid. Okay, let's have a break. Okay, so the remainder of this lecture deals with synthesis and is primarily a review. So even though it looks like it's going to be 7 pieces of vocabulary, only one or two are new, but they're not they're applying known chemistry that you know, to the problem of making amines. So very little new stuff. This is chemistry that is pulled out of the 3A and 3B as we have encountered them. In other words, various methods for making amines were already discussed in various chapters. So what I'm doing now is I'm just pulling them all together and repeat them so you have them all in the same place, and you can place them into the chapter 121 compartment of your brain so you have them all organized. You can also look at the roadmap for that. Okay, so synthesis. The first arbitrarily way of making amines is to make them from other amines, and that's a takeoff of chapter 6, SN2 chemistry. Obviously, SN2 reactions of amines giving you alkylated amines is a way to convert one to make new amines. Okay? So in principle, you could start with ammonia, okay, and make methanamine. Okay? And so the way this goes is ammonia does an SN2 reaction, you push arrows, and you get initially methylammonium bromide. Now in this solution, methylammonium bromide, which is now a mild acid, okay, will recognize that there is ammonia floating around that could potentially be protonated, and of course it will. So you set up a second equilibrium where the methylammonium bromide, which is this product here, reacts with ammonia in an acid-base reaction, and it liberates the methanamine. That's all fine and dandy, but you can see now there's a problem, because we have generated in this process an amine that also has a potentially nucleophilic nitrogen. In fact, arguably this is even more nucleophilic because the methyl is a pusher. At any rate, this methanamine will compete with ammonia for methyl bromide. So we have the old story that we're generating a function in a reaction where the product function can react with one of the reagents that actually generated them. Okay? And so that methanamine will compete and get methylated again. And that gives you dimethylamine, or N-methylmethanamine. And of course, that can be methylated again to introduce a third methyl and so on. So you get actually a terrible mix. Okay? This is very reminiscent. The first time we encountered it this semester was Friedel-Crafts alkylation. Okay? We're introducing one alkyl group. The product competed with the starting benzene for the haloalkane with the aluminum chloride reaction, and you get over-alkylation, polyalkylation. So we also learned that there is a way around it as long as the amine is cheap. Okay? So in the case of ammonia, that's an easy thing done because ammonia is dirt cheap. Okay? Namely, you use the amine in huge excess so that you have, and ideally as a solvent. Okay? So if you use ammonia as a solvent, you'd have to condense it, since the boiling point of ammonia is minus 33, but you can condense it in a flask that's cooled with outside bath of dry ice and acetone. That goes down to minus 78, and that's how you make an ammonia bath, okay, an ammonia solvent. And you can dump in a certain amount of the haloalkane, and you get single alkylation because the product, as it's formed, is surrounded by an ocean of ammonia, and the haloalkane can't find the product in this vast excess of ammonia, so we'll always go for the ammonia. Okay? It just won't see the sky. It's washed out in the large excess of ammonia. That's one way around it. In the case of Friedel-Crafts alkylation of benzene, we use benzene as a solvent. That's also a cheap commodity. It is used as a solvent in many reactions, so we just use it as a solvent, and then the alkyl benzene product won't be found by the Friedel-Crafts reagent because there's so much excess benzene around. So that's one solution. An alternative is to go via nitriles, and so we've seen that one before. So nitriles, remember, with lithium aluminum hydride or with catalytic hydrogen, so hydrogen and metal catalyst, will get reduced to the primary amines. Notice that this is completely selective to make only the primary amine. There is no way there is an over anything, right? I mean, that's the endpoint of the reaction. So that's a good way to make a primary amine if you don't want to worry about over alkylation. Notice that retrosynthetically, nitriles, of course, are derived by SN2 from haloalkanes. Haloalkanes, in turn, can be made in many different ways, from hydrocarbons by radical halogenation, or from alcohols with SOCl2 or PBr3, or even simple HBr or HCl, HX in general, and so on. Okay, so you can weave this back to some simpler species over here. And again, just to drive this in, whenever you see a primary amine that has a CH2 here, that is a prerequisite, you should think of it as remove 4 hydrogens, okay? Dehydrogenate back all the way back to the nitrile. So that's if you think of it, an easy disconnection, and that allows you to introduce that group rather effortlessly. An alternative is from earlier in this semester, namely reduction of a nitroarine. That one